We're now going to take another look at an example of hypothesis testing. In this case, we're going to consider what happens if we do not know the standard deviation of the population. So our example reads, a large university reports that the mean salary of parents of an entering class is $91,600. To see how this compares to his university, a president surveys 28 randomly selected families and finds that their average income is $88,500. If the standard deviation of his sample is 10,000, can the president conclude that there's a difference? At alpha equal to 0.10, is he correct? And so let's begin by looking for a keyword that will help us to determine the hypotheses. The question asks us, can the president conclude that there is a difference? If I'm looking specifically at whether or not there's a difference, then that leads me to believe that my hypotheses will have an equal and a not equal to option. The equal to option meaning that there's no difference, and a not equal to option meaning that there was a difference between the two values. Remember that your null hypothesis, the H sub 0, has to have the equal to option in it. And so the null hypothesis is that the average is actually equal to the 91.6 that was proposed. The alternate hypothesis is that the average is actually different than the 91.6, and so not equal. When we think about the claim, we want to look at what we're trying to show. We're trying to determine if the president can conclude that there is a difference. Remember that there is a difference means that they're not going to be equal. And so we'll write the word claim next to our alternate hypothesis. Step 2 is to find the critical values. And so we begin by drawing our curve. And deciding how to shade. Remember that if we have an equal, not equal to hypothesis, then we will shade on both sides, because we want to consider the idea that it's possible that the average is significantly more, in which case we shade to the right, and also the possibility that the average is significantly less, in which case we shade to the left. Now, they tell us that alpha is going to equal 0.10. Remember that 0.10 is the area of the shaded region. 0.10 is the total area of the shaded region. And so as I look at working this out, I realize that I have two equal sections that are shaded on the curve. And if 0.10 is the total area, then I would need to divide 0.10 by 2 in order to determine the right-hand side and the left-hand side. I know that in order to use table E, I'm going to have to find the area between 0 and the z-score. And so subtracting the 0.05 from 0.5 gives me 0.4500. And looking that up in my table, gives me a z-value of positive 1.65 and negative 1.65. Moving on to step 3, remember that step 3 is the point where we are going to look at our sample mean and place it on the curve. Remember that our population mean, the 91.6, is going to sit right in the middle. And so the question becomes, where is the 88.5? Where is our sample mean in relation to that population mean? And remember that in order to know where to put the 88.5 on the curve, it has to be a z-score. And so step 3 is to convert the 88,500 to a z-score. And remember that our formula to do that looks like this. Now, you may have already anticipated that we're going to have a problem plugging values into this formula, specifically in plugging in the standard deviation of the population. Because if you look back at the problem, what are we given? We are told that the standard deviation of the sample is 10,000. And so what we actually know is that the S value, S standing for standard deviation of the sample, is 10,000. What I do not know is the sigma, which remember is the standard deviation of the population. And so we come to a stopping point with this problem in that we really can't proceed with it because we don't have the information that we need. And so we have to look at an alternate approach. The alternate approach is that if we do not know the standard deviation of the population, then we can't be sure that we're really dealing with a normal curve. And we've seen this issue crop up for us back when we talked about confidence intervals. When we don't know the standard deviation of the population, remember that our solution was to use a different table, and instead of using a z value, to use a t value. And that is what we'll do here as well. And so this is going to change things slightly for us in our process. And so I'm going to go ahead and make a note to myself that if I do not know the standard deviation of the population, then I'm going to need to use a t value to work the problem. And remembering that that comes from table F. So if I do not know the standard deviation of the population, as is in this problem, I need to use a t value and I need to use table F. Okay, so let's think about how this actually impacts our problem. Back in step 2, this 1.65 and negative 1.65, those values came from table E. In actuality, they should have come from table F. All right, so let's go back to step 2 and let's work on fixing this. Okay, so now those critical values will be t-scores, and I'm going to need to get them from table F. So remember that on table F is based on degrees of freedom, which is going to be your sample size minus 1. And before, when we used table F, remember we used the top row for confidence intervals. But we're no longer doing confidence intervals, and so now we're going to use either the second row at the top or the third row. The second row says one tail, and if we're doing a one-tail test, either we've shaded on the left or we've shaded on the right, we'll use that row. The third row says two-tail, and it gives some percentages, which is the case here. And so we're going to look at the two-tail row at point 10. Okay, now notice that this table doesn't require that you split that into two sections. All right, so I'm just simply going to be on the row that says to tail, and I'm going to go over to point 10. So you should be looking at the second column of numbers. And then the sample size is 28, so I'm actually going to go down to 27, which is going to be one less. And I should have as a t-value 1.703. Okay, in actuality, what we have just done in changing the critical value is the only real change in the process. When we go to step 3 now, it would make sense to not say that we're converting it to a z-score, but that we are converting to a t-score. We are going to change our formula just slightly. I'm going to make it t instead of z, and I'm going to make this an s instead of a sigma. But notice that that's the only change on the formula, that everything else is going to stay the same. And so let's plug in. Remember that the x bar is your sample mean. And so we're told that the president surveys the 28 families and finds that their average income is $88,500. And so $88,500 is going to be our sample mean. We know that the accepted mean is 91.6. The standard deviation is 10,000. And the sample size is 28. And again, as you put this in your calculator, you need to put it in with a parenthesis around the top and a parenthesis around the bottom. And it really should go in one step as opposed to doing a piece of it at a time and rounding. And so you'll come up with negative 1.64. And again, if you find that you're having difficulties with the calculator here, then please email me and let me know, and let me talk you through how to enter these into the calculator more efficiently. Okay, so remember now that 88.5 is the same as negative 1.64. And so our job becomes to mark off the 88.5 on the curve and determine whether or not it's significantly different from the 91.6. Remember the 91.6 sits in the middle? The 88.5 is going to sit at negative 1.64, which is going to come in right about here. Okay, so we are comparing the population mean, which sits here, to the sample mean, which sits here. And we're trying to determine whether they are significantly different. Now, granted, they're not the same number. 91.6 and 88.5 are not the same values, but are they significantly different? Remember that the way that we read this table is that as long as our number stays in the part that's not shaded, it's not considered significantly different. As soon as you cross over this boundary line and move into the shaded region, you are far enough away from the 0 to be considered significantly less or significantly more. And so in this case, our values are not significantly different. Okay, so for step 4, remember this is the step where you either tell me that you're going to reject the null or do not reject the null. Remember that the null hypothesis always states that the two values are equal. Specifically in this one it does, but it always says that. The null hypothesis always says the two values are equal. Now, do we agree with that or disagree? Yeah, we agree. We say, that they're not exactly the same, but they're not significantly different. And so we have to conclude that they're basically equal. So the null says that they're equal. We agree. So it makes sense here to say, do not reject the null. Okay, and then step 5, our last step, remember, is to use the chart in our book, which eventually you want to get to the point where you don't necessarily have to flip to that chart to come up with your answer. But right now, if you need to take a look at it, that chart can be found on page 415 in your textbook. We're going to use the fact that our claim was H1, and so we'll look at one of the bottom 2 boxes of the 4. And we said do not reject, so we'll be looking specifically at the bottom right conclusion. And so we'll say there is not enough evidence to support the claim that, and the claim was that the average income is different than 91.6. Okay, so there's not enough evidence to support the claim that average income differs from the 91.6. And so the question said, can the president conclude that there's a difference? No, he really can't. Statistically, it's not less enough. He did come up with a number that was less, but it's not enough to say that there really is a significant difference. And so the answer to that, can the president conclude that there's a difference? We would have to say no. Is he correct? We would have to say no, he is not. And so in conclusion, what you want to be sure that you understand is when to use a z-value and use table E, and when to use a t-value and use table F. Remember that the key is right here. If you don't know the standard deviation of the population, you need to use a t-value, and you need to pull your critical value from table F.